I am Sandeep. Today I am going to solve a question from the Rajasthan Technical University's question paper for the subject Digital Electronics 2022 end term exams. Now the question that I want to take is a 2 marks question, which is question number 3rd, and it asks us to state and prove De Morgan's laws. So the question is actually wrong. It should be state and prove De Morgan's theorems, or you could write statements also. To help you with this, I'll show a book. You can see in the book there are laws, distributive, associative, commutative laws, but when it comes to theorems, there is De Morgan theorem, and there are other theorems also which are very important. Consensus theorem is very important. Then duality, complementary, and transposition theorems are also exist, and then there are all the laws. You should read all about them, you should know about them, so that you can answer the questions that might come from this subject. Continuing with our solution, so what we will begin with is first stating the De Morgan's law. So what De Morgan states is that if we have a literal, then we OR it with another literal, then complement it, we will get the it will be equal to complement of this literal ANDed with complement of the other literal. This is first statement, De Morgan's statement. Okay, this is De Morgan's statement. Then the second statement is if we have the Boolean algebra literal which can take value 0 or 1, this literal, when you have this AND operation, so dot represents AND function, plus represents OR operation. You complement this, then you will get complement of x plus complement of y. So this is the second statement, and this is the first statement. This is how we will answer the first part of the question. Then now, since this is a theorem, we can write the proof. So let us begin writing the proof. To write the proof, first we know that OR operation of a literal will result in something. What will be that? If this is 0, then that will be 1, because it's a complement of that. If this is 1, this will be 0. This always will be 1, because one of them will be 1, and OR logic appreciates a single or more than one. This is a basic identity we will use, and let us say that we can write this like this also. It doesn't matter, variables can be changed until you assign values to them. Now let us start by saying that we know this. This is an identity. We know. You can write we know. You can write this. Okay. Now let us say that x OR with y is a. Then we can say that x OR with y, which is say equal to this. Then complementing this whole should give you a 1 according to this identity. This should be true. This is the first step. So this is step 1 in our proof using this identity. Step 2. Step 2 will be, let us say that we accept or we agree. Let us say that this is true. Okay. Then what will we write? We can use De Morgan's statement to update this identity like this. So we have replaced this function with this because De Morgan says this is equal to this, and we had this here. So we can replace this with this side. since De Morgan says so, and we say, let us say that this is true. Let us say, assume that this is true. If this is true, then this identity should hold, and equation, the left hand side should be equal to right hand side. And if we prove left hand side equal to right hand side, then De Morgan's theorem is right, and hence we have proved that De Morgan's statement is correct. So we are proving for the first one. Now step 3 would be applying distributive law. What is distributive law? I'll just write it down here. Let me write it down with pencil so that sample answer doesn't get affected. So distributive law can be written like this. If A plus BC is written, then we can expand it and write it like this. This is distributive law. Using that, we can expand this and say x or with y or with this, and x or with y or with that should stay equal to 1. Now we know this will give us a 1, so we'll say 1 or with y, and this one reduces to, since y or with y dash will be a 1, so this one reduces to this. Now again, ORing any variable with a 1 will give you a 1, and or same here. And now we have got AND operation of two ones is 1, so LHS has been proved equal to RHS. Hence we have proved the first statement of De Morgan's theorem. De Morgan's theorem or De Morgan's statement is true. It is not a law because it has got a proof. Second statement is this. Let us prove it by using this identity. AND operation of a literal and its complement is equal to 1. AND operation of a literal to its complement will always be equal to a 0. This is the correct identity. We begin here, and let us again say that this is the equality that is ambiguous and we need to prove this. Let us start by saying that we agree, we say that De Morgan's theorem is true. Suppose, let us say that I agree that this is true. If this is true, and if we use this in the identity, then identity should not break apart. So let us say that the identity is this, and let us put A equal to xy. So this function will result in something, and let us say this function is equals to A, as we wrote like this. This function is this, and this function means this is AND operation. Anyway, so not going here and there, sticking to our answer. You shouldn't write this in the sample answer. You just write that this whole is a function, and let us say it is A, then A dot A bar should be equal to 0 as per the identity. So let us write the step 1. Step 1, using this identity, we are able to write that this ORing with its own complement should give a 0. Now let us agree with the De Morgan's theorem and substitute it here. This is equal to this as De Morgan says, so let us use it here, or replace this with this, which is De Morgan's statement, and then it should be equal to 0. This is what the law should ask us to do. Now if we prove that left hand side is equal to right hand side, then we essentially prove the De Morgan's second statement, which is this. Okay, let us start operating. We have again distributive law. What we do is we have this into this, which is AND operation, and again we have this with this. You should have a plus in between, and what do we get? X, Y, Y bar. So if you don't put a dot, it means essentially it means dot, AND operation between all these, AND operation between all these. So X bar is 0 from the identity, and 0 with any literal is also a 0. So basically y bar will be 0 and 0 with y or 0 dot x 0 dot y will be 0 and 0 or with 0 will be a 0. This is basic Boolean algebra which you should not keep writing what they mean. So we have proved again LHS equal to RHS for an identity in which we substitute Boolean equivalent, and thus Boolean equivalent is correct, true, and we have proved that it is right. So this is the answer, a sample answer to university's question in which you have to state. First we have stated these are the statements and these are the proofs to the Boolean statements. Thank you.